Hi everyone. So let me share my screen and we can start on elementary matrices. Okay. So yeah, right, cool. So yeah, now we are going to turn our attention to a special type of matrix called an element matrix. And the first thing we want to take note of is it's always a square matrix. Okay? And we have seen the word elementary before. Where have we seen it before? When we have been dealing with elementary operations and elementary row operations. So, and these two ideas, as we have discussed before, are equivalent. Elementary operations, we utilize these operations on equations. Equivalently, when we take the augmented matrix of a system of linear equation that we have, and once we have the augmented matrix, if we utilize the corresponding row operations for each elementary operation, that's an elementary row operation, right? So yeah, I guess I went in cycles, but yeah, you get the idea. If you are dealing with equations directly, we use elementary operations. The analogous version that we use on augmented matrices are called elementary row operations. So when we talk about elementary matrices, uh we can go from any one of the elementary operations or elementary row operations to elementary matrices. Essentially, to give you an overview, okay, so let me write that down. We have elementary operations, which we perform on equations. And we have corresponding elementary row operations, which we which we which is the term when we use the uh elementary operations on the augmented matrix. Augmented matrix of the equation, right? And then, but elementary row operations, we sort of register the information, like we write down what we want to do, like we are going to multiply the second row by k, or we are going to swap the first and second row, or I'm going to add 2 times the first row to the second row. So we are writing them down explicitly, right? So when we want to look at, but we can also represent this. So we have a representation for this in terms of matrices. So when we look at this matrices that represent the elementary row operations or elementary operations, we have elementary matrices. So that's the idea behind this. Like, that's a very brief overview on what's going to happen and what we are going to see. So yeah, so the first thing I talked about was like it has to be a square matrix, right? And then moving on from that fact, how do we get elementary row operations? How do we derive this? Any elementary matrix, which we'll denote by E, is obtained by applying exactly one row operation to the identity matrix of the same size. Okay, so if we perform a row operation, remember we have 3 of them. We can swap rows, we can multiply any row by a non-zero number, and number 3, I can multiply some multiple of one row to another, right? So if I perform any one of these operations to the identity matrix, I get an elementary matrix. For example, for equation E, for matrix E, I wrote down what is happening over here. This is the eventual matrix that we want to get. But when we start with the identity matrix 1 0 0 1 for the 2-dimensional case, and we swap the first and second row, I will get my matrix E. So here we are doing the swapping operation for the rows, right? Then the second example, the 3-dimensional case over here, shows you the uh the multiplication operation where we can multiply any row by a non-zero constant. So we start with the three-dimensional identity matrix. We multiply the second row by a constant 3, and we will get our matrix E over here. Right? Okay. So I guess the concept of elementary matrices are pretty elementary, right? Like pretty simple. And then for the last case, we are going to look at the last operation where we start with the identity matrix. Since my resulting matrix is 2 by 2, I start with a 2 by 2 matrix. I add -3 of the first row to the second row, and I'll get the corresponding elementary matrix E. And I think there's a typo over here. It should be the second row, not the third row. So just to bring your attention to that. So I've gave you an overview of elementary matrices. We looked at 3 examples of elementary matrices, each one of it which corresponds to an operation that we have seen before. Now to look at the formal definition, let E be an n times n matrix. Then E is an elementary matrix if it's the result of applying one row operation. And we want to apply just one. We do not want to apply like a sequence of row operations to the identity. So it's just we have one elementary matrix, exactly one for each row operation that we do. So and then there's a special name for the elementary matrices which we get matrices derived from the first operation, derived from the swapping rows, and that's called the permutation matrix. Because you'll see that we can permute. This leads to a permutation of vectors when we multiply this matrix, or permutation of rows, right? So what is the advantage of this? I'll cover that. Like, why are we introducing this concept? We don't want to just talk about concepts which has no utility, right? Like, it's useless if a new idea doesn't bring anything that is advantageous to us. So this allows us to express everything that we have been doing so far in terms of matrix multiplication. So you'll see this later on, but all the operations that we have been doing for, if we can write it down as a matrix, it will simply be matrix being multiplied to each other, right? And then that will be far easier to keep track of, and we can apply concepts like taking the inverse of an elementary matrix and stuff like that, so which we'll look at later on. So and this is the key idea that I was talking about earlier, right here. Elementary matrices can be used in place, so we can replace row operations, and that turns out to be very useful, as we'll see later on. And multiplying, and this is important, on the left side by an elementary matrix will have the same effect as doing the row operation to obtain E. So it's very important to multiply elementary matrices on the left, not on the right. So that is encapsulated here. To perform any one of the 3 row operations on matrix A, it suffices to take the product EA, where E, so we are multiplying E on the left, and E is the elementary matrix that's obtained using the desired row operation on the identity matrix. Yeah, okay, so let's look at each case individually. So now we are looking at swapping rows. So and again, when we look back at the top, elementary matrices which involve swapping rows are called permutation matrices. So that's something that that's why we are talking about permutation matrix now. So that's something that you need to take note of. So let Pij denote the elementary matrix which involves swapping the I and jth row. Then Pij is a permutation matrix, and if we apply it to matrix A, we'll get matrix B, which is equivalently obtained from A by swapping P, rows I and J. So this essentially tells us that, so let's say I is 1 and J is 2, right? So Pij, P12 is the elementary matrix which swaps rows 1 and 2, right? And so if we derive that from the identity matrix, I would get P12 is going to be, I want to swap rows 1 and 2, so I would get 0, 1, 0, 1, 0, 0, 0, 0, 1. And this theorem tells us that if I have matrix A, for example, A11, A12, A13, A21, A22, A23, A31, A32, A33, and we multiply P12 to A, that has the same effect as me directly just swapping this two rows. So if I call that matrix B, A21, A22, sorry, let me write that above. A21, A22, A23, A11. So this is my first row, this is my second row, because I swapped the original row 1 and 2s, right? So if I multiply matrix P to A, that is equivalent to me just directly swapping rows 1 and 2. That is what lemma 2.45 tells us. So, and that's what we are going to do in example 2.46. This is the permutation matrix that we derived earlier. We swapped the first and second row of the identity matrix. After swapping row 1 and 2, we get this P12. And here I used an example where A is a 3 by 3 matrix, but here A is a 3 by 2 matrix. And you can see that if we do matrix multiplication, P12, okay, so if we do P12 times A, that's essentially, I would get this matrix B. But if we study matrix B, we can see that B can be derived from A by swapping the first two rows. So what I'm trying to say right here is multiplying A by matrix P12 is equivalent to just directly swapping the rows of A, which is what the theorem was telling us about. So now let's look at scalar, like multiplying a row by a scalar. So I'm going to use this notation. This notation is going to be standard throughout the textbook to denote the elementary matrix corresponding to a row operation where we multiply the ith row by the non-scalar k. So if for the two-dimensional case, 2D case, I have my identity matrix I, and if I multiply the second row by 2, I would get 1, 0, 0, 2, and I'm going to label this as E. K is going to represent my scalar, and the second number is going to represent my row, right? E22. So this is going to be my scalar, or the number k that I multiply by, and this is going to be my row number that I multiply the k to. So we explore this lemma. Okay, so yeah. And this equation tells us that essentially if I apply this E to any matrix A, that's equivalent to multiplying the ith row of A by K. And we'll look at an example to demonstrate this. So if I have a 3x3 matrix, a 3x3 identity matrix, and the first index is my scalar k, that tells you the multiplicity constant, and this tells me the row that I'm multiplying k to. So I'm multiplying the second row by k, and then since I'm multiplying the second row by k, I would get this matrix E. So this is E52. And I have matrix A, which is the same matrix. And by matrix vector multiplication, matrix multiplication, we can see that we will derive with this matrix. But this matrix is exactly just matrix A, where second row is being multiplied by 5. So yeah, we can see that multiplying matrix A by our E52 elementary matrix is equivalent to just multiplying the second row of matrix A by 5. So yeah, let's go on to the last operation. So the idea here is pretty straightforward again. It's just here I'm gonna add k times the ith matrix to the k times the ith row to the jth row, and yeah. So for example, over here, I'm going to multiply 2 to the first row and add that to the third row. So if I'm starting with this identity matrix, 2 times the first row gives me this row over here. And if I add that to the third row, I'll get 201, which is what I have over here. And the idea is the same. If I multiply this matrix E to A, is the same as me applying the doing the row operation, adding 2 times the first row of A to the third row. So yeah, now we have seen that for each of the actions, the row operations that we have seen, we can actually derive an elementary matrix, right? And applying the elementary matrix to our matrix A is the same as doing the original row operation to matrix A. So yeah, now let's look at the next idea where we want to talk about. And this idea tells us that we can undo row operations. So we can undo row operations. So the key idea here is that for every row operation, we can undo it. I meant undo. So that means there is an inverse. And the idea is pretty intuitive, right? If I swap row 1 and 2 to get back the original matrix, I can unswap row 1 and 2, right? So I just swap it back. And if I multiply, for example, the second row by 3, how do I get back the original matrix? I multiply by 1 over 3. And that would negate the effects, right? So yeah. So that means in mathematical language, every elementary matrix is invertible, and it's more importantly, its inverse is also an elementary matrix. Because let's look at the idea that I talked about earlier. If I'm swapping 2 rows, we know that there is an elementary matrix for that. And if I want to undo the swap, I have to swap back, right? So this swapping back, so if I swap row 1 and 2 to go from, so let me write this down. So if I matrix A and I swap row 1 and 2 to get matrix B, this can be represented by an elementary matrix. And I think that the notation that we used above was EKI, right? P12, right? Okay. So Right, let me yeah, okay, so I think this is was okay. So this will be represented by matrix P12. And now if I want to undo that, so if I had, let's say 1, 2, 3, 4, and I swapped rows 1 and 2, I get 3, 4, 1, 2. All I have to do is swap row 1 and 2 again. And what is swapping row 1 and 2 is exactly this elementary matrix again. So the inverse of an elementary matrix is also an elementary matrix. So that's an important fact that we want to know. So looking at the three examples here, let's walk through this together. The inverse of an elementary matrix is constructed by doing the reverse row operation, right, on the identity matrix. So here is the identity matrix I. So if E is obtained by swapping, if our elementary matrix E is obtained by swapping rows I and J, E inverse is also obtained by swapping rows I and J. So if we switch the rows, we switch back. If elementary matrix E is obtained by multiplying row I by scalar K, E inverse is obtained by multiplying the same row with the fraction 1 over K. And if the elementary matrix E is obtained by adding K times row I to row J, yeah, K times row I to row J, the inverse is obtained by subtracting K rows. Yeah, subtracting, sorry, K times row I to row J. Sorry, give me a moment. Let me stop sharing. Okay, great. I'm still recording. I just want to make sure I was recording. Okay, cool. Yeah. So this is how we obtain the inverse of elementary matrices. So let's look at this example 2.52. So here my identity matrix, sorry, we start with the identity matrix I 1 0 0 1, and we can see that how do we get E? I multiply row 2 by 2, right? So I'm applying E to where this is the scalar and this is the row. So how do I get the inverse matrix? I multiply the same row, I 1 0 0 1, by 1 over 2. So this would be my row 2 by half. So that will be my inverse matrix. And we can actually verify that E times E inverse is I, and also E inverse E is I. Okay, so yeah. All right. And then so here comes the advantage of doing elementary row operations or elementary matrices. So suppose we have a matrix that's row reduced to its reduced row echelon form. By tracking each row operation, this row operation can be completed through multiplication as elementary matrices. So we can actually register, like we can uh register the sequence of row operations that we do to matrix A to get its reduced row echelon form as a series of multiplication of elementary matrices. And so essentially, if B is the reduced row echelon form of A, we can write B equal to EA where U is the product of all elementary matrices. So yeah. So let me go through 2.54. Let's see. Okay, so yeah, so we have example 2.54. Okay, so let A be this 3 by 2 matrix here. We want to find B, the reduced row echelon form of A, and write it in the form of B equals to UA. Recall that U is the product of all elementary matrices. Right? Okay, so to find B, we want to row reduce A. So for each step, we will record the appropriate elementary row matrix. So the first thing they want to do is swap rows 1 and 2. So if they swap rows 1 and 2, we get this matrix, and the resulting matrix is equivalent to finding the product of the permutation matrix, right? And this is derived from our identity matrix. And A. So this is the first elementary matrix. I'm going to write it as EM. And then, so first EM is P12. So how it goes is we are applying P12 matrix multiplication on the left to A. Okay? And then next we add -2 times row 1 to 3. So this is going to be E -2 times 1 plus 3, right? So we have that matrix next. So we have E -2 times 1 plus 3, P12 to A. So this is how we register the sequence of elementary matrices. Okay? And then uh yeah. So then we have this uh there's a typo here, right? So this should be 3. 3, 3. So when we when we multiply these two matrices, I will get U. Because we want U to be the product of elementary matrices. So yeah. We stop here because this is in our elementary row echelon form, a reduced row echelon form. So yeah, all we have to do is we only have 2 row operations, so we only have 2 elementary row operations. So now we have to multiply this 2, and the multiplication is pretty easy. So yeah, uh, okay. So here we want to find an easier way to find our matrix U, right? Because the step that we just did is reliable and simple only when we have a few operations. But if you have like 10 or 20 operations, then it's gonna be very tedious. So the next theorem gives us an alternative way to find U. So it gives us a way to find the product of all elementary matrices directly. And this idea is going to be the same way as we find the inverse of a matrix A. So essentially what we start with an augmented matrix with matrix A, the original matrix, and then the identity matrix. Our idea is to reach matrix B. So the only difference is for the inverse matrix, we try to reach IN when we want to find the inverse of A. But here we want to reach B. So in this case, we know matrix A and we know the reduced row echelon form. So then this theorem tells us that what we have on this side is our matrix U that we need to find. All right. So yeah. So yeah, we just revisit the previous example. We start with matrix A. This is my identity matrix. We know that matrix B is going to be 1 0 0 1 0 0. Let me just check that. Yeah. And then this is identity. So I want to reach a point where I have 0 1 1 0 2 0. This is my identity matrix. And that would lead me to something like 1 0 0 1 0 0. And whatever is here is going to be my matrix U. So like how we did finding the inverse, we row reduce the matrix on the left side and we apply the same operations on the right side. So yeah. Um uh let's see. Okay. So now let's go through this, and I think that would be the last part of our lecture. Yeah. Okay. So okay. So going back to what we did in the when we looked at the inverse of matrices, right? We deduced that we reached a point where we were talking about a matrix A being invertible if and only if we can reach the identity matrix IN using our row operations. So it's like what I was talking about earlier. We start with something like this. I want to reach a point where I have IN and matrix, some matrix here. So if A can be row reduced, we perform elementary row operations to reach the identity. This matrix is called the inverse of A. But if we cannot reach that, then A is not invertible. So we discussed this towards there was this entire subsection where we did finding inverses of matrices. So that's where this was discussed in. And this leads to an important consequence when we are looking at elementary matrices also. So suppose we have an invertible matrix. That means there exists a matrix B such that A times B is the identity matrix. So we set up the matrix AIN like this, and we row reduce to reach the form in this form here. And when we compare this to the example we just did, in the example we just did, we did not want to reach this point, but we wanted to reach B something, right? So yeah, in this case, what we want to apply is just that if B is the identity, right? That means what we have here is yeah, so if I guess this is a very convoluted way of saying that okay, so scratch everything I said. When we are looking at inverse matrix, essentially all this stuff is just like going around in circles. And but the idea is very simple. When we are looking at computing inverses of matrices, we apply elementary row operations to reach the identity matrix, right? Each of these elementary row operation can be, we just studied in this chapter, that can be represented as an elementary matrix. So that means that I can just apply row operation 1 all the way to row operation k in order to get the identity matrix. So yeah, that just means that the product of the elementary matrices times A can give me the inverse if A is invertible. And this implies that A is, yeah, A inverse is just the product of all the elementary matrices that we get when we take the when we take the okay. So let me rephrase this. So A inverse is going to be the product of elementary matrices. And how do we obtain these elementary matrices? We take the matrix representation of all the elementary row operations we did when we discussed algorithm 2.37 in the previous subsection. So yeah, that's what this entire thing is saying. But it's making it unreasonably complicated. So yeah. All right, cool. Uh and then from there we can go one step further, right? So since A inverse is the product of some elementary matrices, if I apply inverses to both sides, I will get A inverse inverse that's equal to this. And the inverse of an inverse we studied under the properties of inverse matrices, that's equal to A. And we know that if I'm applying the inverse to a bunch of matrix multiplication, I need to reverse the order, right? So we covered all of this under properties of inverses or inverse matrices. So this just tells you that if A is an invertible matrix, if it can find the inverse of A is just a product of elementary matrices, right? So that's what this theorem tells us. So we just go one step further from what we discussed in this section over here, this paragraph over here. So now let's look at a concrete example. Okay, so we are given this matrix A and we want to write it as a product of elementary matrices, right? And we just discussed that this only holds if A is an invertible matrix. So the idea is we want to find the elementary matrices. What we want to do is from the previous theorem, holds when A is invertible. And so what we want to do is we want to start at this form. So since A is 3 by 3, I have 0, 1, 0, 1, 1, 0, negative 2, 1. This is my matrix A and my identity matrix. And I want to apply elementary row operations till I get the identity matrix here. So this is my identity matrix and some other matrix here. So what does this tell me? Because each row operation has an elementary matrix, I can state that the bunch of row operations multiplied to A will give me the identity. But this also means that the inverse of A is actually just this matrix right here, EK minus 1. I'm assuming that there are k number of row operations. That's why I have E1 up to EK, each associated to one row operations, or one row operation, right, out of the k number of them. And if I apply the inverse to both sides, I would have A, E1 inverse, E2 inverse, up to EK inverse. And this is what, and I just mentioned that if you're not sure about what's going on here, I just applied the properties of the inverse matrices, right? So that's towards the end of, I think finding the inverse of a matrix subsection. It's just before this or right before that. So right before this subsection or the one before that, right? So yeah. And that's what essentially we do here. We set up the matrix AI, the augmented matrix AI row reduce, and we record each row operation as an elementary matrix. So yeah, this is AI. The first thing that they do is they swap the first and second row, so they represent that by this row matrix. And then what they do is they they subtract um row 1 from row 2. So we have -1 times 2 plus 1, and that's represented by the elementary matrix E2. And then finally they add 2 times row 2 to row 3, right? So that's represented by 2 times row 2 to row 3. So this represents row 2, row 3. And then we get uh the identity matrix, and this is represented by this elementary matrix. So we have 3 uh elementary matrix. So we have we did E1, we have we did E1 first, E2 first, E2 next, E3 third, and then we have I, right? So yeah. Um so let me write it down. E3, E2, E1, AI. So E1 comes first because it's the closest to A because we did that first. And we applied E2 after we did E1. And we did E3 after we did E2, E1 and E2. So that's why E1 is the closest to A, and then it's E2, and then it's E3. But this is my matrix. E1 times E2 times E3 is okay, if I say it from left to right, E3 times E2 times E1, that's equal to U. So U is E3 times E2 times E1. So this means that we have UA equal to I, right? And then we apply one of the properties of inverse matrices. And we just studied that each of the elementary matrix has an inverse, right? So we do the appropriate inversion, and then we would get our matrix A. So yeah. All right. So with that we have come to the end of this subsection, and with that this chapter 2. If you have any questions, just email me. If you want to meet me over Zoom to clarify some questions, we can always set up a time. So yeah, just send me an email if you have any issues. From the next video onwards, we will be starting with we still need to cover a little bit of chapter 1 where we talk about Gaussian elimination and stuff like that. And then yeah, we'll move on to more interesting stuff.